questions before we go on?
And I guess there must be more confidence.
Yeah.
Questions? Suggestions? So if I'm going too slow, please let me know. If I'm going too fast, please let me know as well. Okay, so now a bit more practical. So if you have your data, and if you have decided on a number of models, of course, as I've said in the very first part, first you would have your data cleaned and explored, and you would have the scientific and statistical questions that you would ask already clarified. So this sets off once you have, say, pre-selected a number of models that you would like to check. What do you do there? Right, so first, just as a sort of recipe to do that, what later one might do implicitly, but also which models, in some sense, the code flow in the toolboxes that we're going to see. So the first one would, of course, define what do you want to do, what do you want to predict. And in actual data, there is not necessarily an obvious target of prediction. When some of the benchmarking data sets come with a label to predict, such as the IRIS data set, but you could also think of, say, can we predict pittle from Sibyl or something, knowing also the species of the IRIS? That is also a valid scientific question, say, to ask in that context. So this define the prediction task actually also requires a bit of thinking about what you actually want to do, what you actually want to infer and conclude from the prediction experiment. Then the second point, which we've already partly discussed, what shall be the measures of goodness, or the measures of goodness of prediction? Usually there is a standard selection of measures that one would use, though also this might depend on the scientific question you're asking, and I personally would recommend to use more than one measure of goodness. I will come to that in the regression setting later on. And also, of course, you would not only assess a model by a single measure, but also once you've seen an interesting model or seen that some models perform best, you would also have a look at model diagnostics in standard linear regression. Okay, then this is usually the computation most intensive part of your prediction experiment. You would actually carry out the estimation, and for that you need to specify by which means you estimate the expected error of prediction. Usually it's done by one of the standard resampling strategies, which I will also explain in a moment. And from that you get the table which we have seen, say, in the IRIS dataset experiment, or the table that we have seen before the break, where you have your methods as the rows or columns, and the model goodness in the other ones, or the column or the rows. But then the experiment isn't complete, since to make a scientific conclusion you need to have specified a scientific experiment that can tell you yes or no. So if, say, your hypothesis was model X can predict better than a random guess, well, then you will have to compare it to the random guess by quantitative means. If your hypothesis was model A was better than model B on this particular data set, then also you will have to make an appropriate comparison or hypothesis test. In its simplest form, you can compare, say, error bars or confidence intervals, whether the confidence interval for one model is overlapping with the estimate for the other model. Of course, always being careful about multiple comparisons and the usual statistical pitfalls. And in this validation setup, you should also be careful to validate out of sample if the experiment is really to be about predictive goodness. And comparison to naive baseline should also not be forgotten. It's one easy to commit error not to compare against a, say, surrogate for a random guess, such as predicting the training mean, since if you conduct your experiment and you see, okay, model A is better than model B, but both are really much worse in the state of the art of the random guess, then the conclusions have not made that type of comparison. You want to be better than random is, because that tells you that using the data, using the features has been of use at all.
When you say random guess, you said uninformed guess.
We'll come to that. So there's certain, it would depend on your performance measure, but there is, for that given measure, a best uninformed predictor. For the mean squared error, it would say predict the mean of the training labels. For in classification, if you are talking about misclassification error, in terms of misclassification error, the best uninformed predictor would be predict the majority class. Say if you have 70% of one class and 30% of the other class, and you want to minimize your misclassification error by not using anything about the features, you would want to predict the 70% class, which will give you 30%, only 30% mean misclassification error.
Can I ask a question?
Yes.
What is the difference, because you said sometimes we don't know what we are trying to predict, so what the variable or data is, but then what's the difference between that and unsupervised learning? Because I believe it's all supervised learning, because that's where you don't have a target as well.
Well, this is the difference between not having anything to predict and not knowing a priori what you want to predict. So in supervised learning, you fix. So the label you predict may not be unique given your scientific question, but it will be something. Whereas in the unsupervised setting, you don't have a label at all that you have settled on that you would want to predict. More questions? Okay, measures first for regression, since I think there is less ambiguity and variations on that theme. That's why I've decided to start with regression. So in regression, the measures are usually derived from the distribution of prediction residuals. So prediction residuals being the true label minus the predicted label. So that's how design is taken usually. Though you take most measures are actually functions of the absolute value, so it doesn't matter. So three measures that you see most often is the mean squared error, which is the mean squared residual. Mean absolute error is the mean absolute residual, and the root mean squared error, which is the root of the mean squared error. So it corresponds to the residual standard deviation. So as you will see, mean squared error and root mean squared error actually describe the same thing. The mean absolute error describes a different thing. So if you know one of these two, you know the other, but you do not necessarily know the MAE. So why is there the root mean squared error? So they have the same unit. Root mean squared error and mean absolute error have the same unit. So since the one is based on the absolute error and the other one on the squared error, the root mean squared error is more sensitive to the tails, meaning more sensitive to outliers. While of course both are in some way sensitive to outliers since they are means and not quantiles. So I usually in regression experiments report the MAE and the root mean squared error since they are on similar scales. Now error bars, will come to that in more detail tomorrow. So how you precisely obtain them, or what's the best way to obtain them, or how to do hypothesis tests is subject of ongoing research. But I would argue there should be at least some way in which you obtain them, otherwise you don't really know whether your numbers are different. So in a large sample setting you might argue, well, we're so small anyway since my test set is so large. If you have 200 samples or 1,000 samples, which is not a rarity in a practical setting, then you really would want to have some version of error bars that is also statistically properly justified. Now some other measures of predictive goodness that you might find, so R squared out of sample, when you find it not so frequently, but as I have said, this is not necessarily a bad idea, though one would like to know what exactly happens if you divide by a random variable the medians. In instead of means. So medians, of course, or quantiles in general, less sensitive to the to outliers in the tails, and variance unexplained, in essence being the r squared without the 1 minus. So r squared out of sample can actually be also negative. It's only guaranteed to be 0 or bigger if you compute it in sample. Out of sample it can also be negative. So if you predict the mean and you see a negative r squared, that's not necessarily wrong. Variance unexplained just gives you a fraction, just gives you the fraction without the 1 minus that seems to be, if you look at it in that context, somewhat arbitrarily in the r squared. Other measures, so you occasionally find other measures in application literature, but they are rather uncommon. And since this whole thing is the endpoint of some estimation process, so the whole thing is random, if you do an arbitrary thing, then it might mean that the statistic might just not mean anything because there's so much noise by how you compute it. So without really studying what is going to happen, I would recommend to be careful, at least using any measure other than those mentioned on the slide for supervised regression. Any questions? So quantiles especially are, so they're not necessarily problematic. I mean, they're stable to outliers, but there is not much research in the asymptotic and how randomness affects the estimation of quantiles in a predictive setting. So if you say look at number of data points in the top quintile or something like that, it is not entirely clear how sensible this will be with respect to noise without further studies. Questions? Okay, so these are MAE and RMSE are going to be the two measures that we will use in the workshops. Now, how do we estimate? How do we estimate the expected prediction error of a prediction method? So the one blueprint that one should keep in mind is a slightly more stylized version of the data splitting part. So if you remember, we had the generalization assumption here. We feed this in the predictor and we get predictions, residuals, and from the residuals we can estimate the measure of prediction goodness. So this is the core of the estimation process. Now for reasons of scientific cleanliness or scientific accuracy, one would want to test all predictors using the same split, right? So by Mills' method in separating modes of influence from each other, if these would be different training and test splits, then a difference in the result would be explained either by the different split or the different method. Hence, applying Mills' method cleanly here means that you want the same split for all of the method, and that also, in a second step, gives you paired samples of residuals, since the points predicted were the same. Hence, you get paired samples with the possibility to do, say, paired sample tests on the residuals between the methods. It's important. Now then, for reasons that are mathematical and have to do with increasing the accuracy of your estimate, about which we will talk again tomorrow in the theory lecture, in so-called cross-validation or resampling, you repeat this whole model comparison experiment with multiple splits. So how you choose the splits will be explained on the next slide. But training and the test data are different in each repetition. So one data point that goes in the training set in one repetition might go in the test set in another repetition. So you will get, for each model and each split, possibly multiple performance measures. Now you would want to aggregate the performance measures from the multiple splits in one, and this is usually done by computing the mean of the performance measures in the multiple splits. So that has, as I said, mathematical reasons. Resampling reduces the variance if you repeat the experiment, if you repeat the resampling of your data in training and test and then take the mean. So it's a common principle that we will see when it comes to cross-validation, but also when it comes to ensemble methods, which are also going to be run on multiple versions or resamples of the data set.
So this tells you something about the stability of the model.
Well, it does. So it could be used to tell you about the stability of the model. However, it is usually not used to get an estimate on the model stability. So the randomness inherent to the model itself, as opposed to the randomness in the split of the training and test data, and it is also an open question how to incorporate that in the estimates of model uncertainty. So what this primarily gives you is for each model an estimate of model goodness, and the confidence interval estimated from this will give you an estimate for the error of estimation on a test set of a certain size, rather than an estimate for the stability or for the variance in rerunning your model, which are slightly different things, though they could be estimated with strategies that are similar. Okay, question?
You see at the bottom, are they three different splits or are they the same split? Because each one says split number one.
So split is a split in training and test. So in the bottom figure there are three splits. So a split consists of folds, two folds. So the training set is sometimes also called the training fold and the test fold. Or sometimes fold is only used to denote the test set. As in K-fold cross-validation, the union of the test sets is the whole data set. So yeah?
I think there's a typing error, right?
Yeah.
Because the first one says on split number one, the second one also has on split number one.
Oh yes, they should one, two,
One,
three.
two,
Ah,
three.
there's a
Yeah,
typo.
yes.
All right. Oh, that's weird. So I've shown this slide a huge number of times also to my lectures and no one noticed that.
Do we get cookie points or?
I think there's cookies outside. I have some of my hand.
Go collect.
Yeah, thanks for this. I need to remember this. Cookie points if someone reminds me and I've forgotten. Okay, so popular ways of resampling your data, which really means that they're popular ways, then there is some ongoing research, though not much of it, on what the best way to resample is. So the errors and the variances. So the errors are usually aggregated by mean, which is the way that comes out of the variance reduction rationale. The standard errors or variances also should be aggregated by mean. So sometimes you find that the standard errors are computed as a standard error of the resamples, which is not a good idea. I'll come to that tomorrow. Now, popular types of cross-validations. One is K-fold, which is probably the most frequently used. Your data is split in K almost equal parts, and those parts are going to be your test sets. The training sets are going to be the complements of these K parts. So there is one paper which I think uses a few data sets from the 90s, which has analyzed the goodness of estimation versus number of splits, and it says, okay, 10 is good on that data set, and since then a lot of people use 10 for k. So, I mean, since that is not really a exhaustive comparison study, it's not entirely clear whether that's really the thing one ought to do. Also, in terms of prediction, estimating the error statistic versus training the model, that might be just completely dependent on the size of the data set. But k equals 5, 10, or 3 are popular choices for reasons not entirely clear to me. So why 9 is not a good choice, or 7 is never used. Anyway, leave one out. Leave one out is k-fold cross-validation, where there's always a single point in the test set, which leaves you with as many folds, as many splits as there are data points, which, thinking about the computational issues, means that this is, you estimate the model as many times as there are data points, but for some types of models, there is fast ways to compute the out-of-sample error. In that case, for example, for least squares based models, or for some kernel type methods, so for linear regression, since the 70s, it is known that you can compute the mean squared error explicitly. For leave one out cross-validation, it's called Allen's press. So, and that extends to a number of related methods as well. So if your data set is large, yes?
So what's happening there then? You leave one out of the 5? Or?
Yeah, so the test sets always consist of one data point. In every data point occurs once.
Only one?
Only once. Which gives you issues, because then you have only one residual per test set. Now, how do you estimate your error if you take the mean?
Yeah.
So you get a degenerate variance estimate from that. It's not clear how you get a proper variance estimate from leave one out.
Then I would say just don't use that one, right? Or
It makes sense to use that one because there is quick. So I mean, it might make sense in two scenarios. So one of the reasons is there's explicit formulae to compute the leave one out error, so they meet the estimate of the error itself, as opposed to its confidence interval. Now, the leave one out uses the maximum of data to fit the model. So if you actually do not use it for model evaluation, but for model tuning as to select a parameter, which we'll talk about tomorrow, doing leave one out might actually make sense. Though, again, the complete implications are not fully understood. So if you use leave one out for tuning, and then say k-fold for estimating the final error of the strategy, that is a combination that actually seems to make scientific sense.
Because for time series, that makes a lot of sense as well, right? I mean, you wouldn't be able to use necessarily k-fold for time series because.
Well, time series.
Well, and then it's like walking forward in time.
But if you walk forward in time, if you do leave one out, some of the points you leave out will be the past of some other points in the training set.
But then you're less sensitive to regime changes, for example. You know, the
Yeah,
market.
but then you're not forecasting.
Huh?
If some of the points you predict are in the past of other points you predict from, it's not forecasting anymore because you're predicting the past.
So I'm not sure I understand that part. So what basically, I mean, in k-fold, what I understood is that it randomly samples,
Yes.
right? But then, exactly, you're trying to predict, say, a market move, if it's gonna go up or down, right? You can't just use data, randomly sampled,
Yeah.
because then you need to kind of
Yeah,
track
sure.
the-
So if you're in a time series context, you do not want so if you want to do prediction that is also temporal,
Mhm.
you wouldn't want to use a tested training split where some points in the test split are in the past of points in the training split. And then there's the added problem that if you do a full test split, there will be some points that are further in the future. So you would want just to predict ahead with a fixed horizon. But then you run into the problem, how do you get a selection of test points which is independent? So I mean, you don't get this anyway because there's this covariance issue, but maybe you can say not a sliding window, but you jump ahead a little bit and things are sort of independent, and but this would not be leave one out in the sense of this. This would be forecast one point ahead with a sliding window, say, or with a fixed horizon. There is resampling schemes for time series that essentially people in finance have thought of. Though I will come back to that when I talk about the advanced topics, but it's not entirely clear what that estimates. So how much error do you make because the data are correlated versus what is estimated. So which part is correlation, which part is really the merit of the method. So as you have correlation, in practice, you will underestimate your errors. So you will be falsely optimistic when you assess methods, which will make you discover merit of a method more often than not, if compared to if you would have a fair assessment method that knows everything about the generating process. So you will discover differences more often if there's correlation in your data. Right.
So that a good practice is to use Lib1 out for model tuning, and then follow up with K-fold for validation. Right?
Yeah, that's a sensible way, or K-fold for both.
So my question is, but then you run FIP. So then effectively you will be in a situation where you don't have an out of sample.
No.
Because if you apply K-fold for training.
We'll talk about that tomorrow. But essentially, you would split the data in 3 parts. On 2 parts you tune, on the 3rd part you evaluate the whole strategy.
Oh,
And
okay.
the whole thing is then nested. And that makes it slightly difficult to explain, hence I will do that tomorrow.
Okay, I thought you were talking about just one data set, and that's okay. I understood.
No, just all on one data set. Everything is on one data set.
Yeah, but then you need to split it in 3 parts.
Exactly, so the
tune
resamples will be
go.
nested, but still it would be coming from one data set. Okay, and if you have large data samples, the last method, repeated subsampling, so just to sample a training or test at the specified size, especially helpful if you have a huge data set which you don't want to load all, or if fitting your method to a training set of size k divided by k plus 1, which is the majority of the data, is not feasible. Sorry. So some of you who are familiar with machine learning may notice that one type of resampling is not listed here, which is Efron's 0.632 plus Bootstrap. So I have not listed it here for 2 reasons for the experts. So first, about cross-validation is, I think, in its very statistical version, studied since 30, 40 years. And then there is results about the error of the cross-validation estimate itself, though not as satisfying as one would or might like. We'll come to that later. Whereas the 632 plus Bootstrap, there do not seem to be, so apart from the original papers which proposed the method, there don't seem to be extensive studies on the goodness of the method. So that Bootstrap suggests to resample data with replacement, which seems to be a bad idea if you do nested resampling for tuning. At some points in the nested sample will end up in the training and test of the validation split. So if you don't know what I'm talking about, don't worry, but that's for the experts. Yes?
But you see bootstrapping all over the place, right? Or
So it's not entirely clear what it does. That's somewhat disconcerting. And so no, bootstrapping is a different thing, right? So bootstrapping for estimating, say, standard errors, or bootstrapping for estimating the bias, bootstrapping for tuning, that's perfectly fine thing to do. So there is theory on that. And so bootstrapping or the jackknife is standard stuff. But the particular 0.632 plus bootstrap that suggests the estimation of the cross-validation error as a weighted mean of the training and test error claiming it is more efficient in using data has, in my opinion, not been researched to an extent that it would be safe to use in this context. So for tuning, you can use anything as long as the validation and error estimation is statistically justified. I would be careful about the 632 plus. 632 plus, because that is the weight. That is the weight in the weighting scheme of obtaining training versus out of sample. So also how they arrive at this weight is slightly heuristic. So using a heuristic tool in assessing the goodness of your method seems a bit old to me, unless there is of course justification. So, any questions?
Sorry, what is the difference between repeated subsampling and K-fold?
So in K-fold, the test sets may not overlap. Whereas in repeated you can introduce this as an additional condition, but in repeated subsampling, this non-overlapping condition does not need to be there. Also, training and test set together do not need to be the whole data set. So you could say, okay, both, if you have a billion data points, you can say, okay, training and test sets are 10,000 large. And I have a billion data points, so I can choose a new training test set anyway, always, and I don't need to resample, I don't need to use my data efficiently, so I can just resample 10,000 each. Why not? I mean, you cannot do that evidently if you have less than 20,000 data points. This is one very simple strategy if you have big data and you don't. The asymptotics of the estimation of the test error, there is 1 to the square root of size of the test set. So if you have huge amounts of data, then whether you use 10,000 or 100,000, I mean at that point it doesn't matter much anymore usually. So quantitative comparison, last point in the validation workflow. How do you actually compare the models once you have the table? Right. So strangely, much on this point is still open. There was a strain of research originating at Efron and later carried on by Hasty and Tipshirani. There was a strain of research by Yoshua Bengio, which ends in 2006, quite abruptly with open questions, and starting after that, I think started focusing completely on deep learning, abandoning this quantitative comparison. So what is known, some things are known, but a lot of questions are open. So if one really wants to be quantitatively solid, one has to work with incomplete knowledge on this side of the in practice. So it is not entirely known, for example, what the best way is to estimate the error of the error statistic. I mean, there is a number of ways that could influence it. So the resampling setting, right? How do we resample? How it defaults? Then how many residuals are there? How do we use the residuals from the different folds combined? And there can also be randomness arising not only from the split, but also arising from a method which is non-deterministic, such as neural networks or random forests. Random forests already have the random in the name. So how do we put all of this together? It's not entirely clear or completely studied. On the statistical side, there's the problem. If you do cross-validation, you are reusing the data. So if you do a complete split of your data, each error statistic is computed from the same set of label feature pairs. Sometimes they come in through the test set, sometimes they come in through the training set, but they both go into the error statistic. So the samples from different folds are correlated, and how to account for that correlation, or whether that is possible at all if you use the K-fold scheme, is not entirely clear. But but there is some ways to pay with number of samples and still be on the right side. So what does the right side mean here? So in a practical setting, spotting an improvement or spotting a difference is usually more severe in terms of conclusions than seeing none. Meaning that the type error, spotting a pattern where there is in reality none, is more problematic of the errors as compared to the type 2 error, which means not spotting a difference, say, between methods or pattern in the data where there is one. So if it is not spotted, you can maybe spot it if you have more data, whereas if you spot something while it is not there, it might lead you completely astray with your conclusions. So I would argue in a practical setting that is about the data and not about the method, it is more severe to find a difference or to find a relation that isn't really there. So one can err on the side of caution by employing conservative estimates, say using the bootstrap and then aggregating conservatively by the mean. So here is the bootstrap for estimating the standard error that can be applied there. So jackknife is quite easy to compute and applies and is okay for most measures, though if you have quantiles in your error measure, you want to use the bootstrap and not the jackknife, because the jackknife doesn't give you an asymptotically correct estimate. So more details on that I will show in the theory lecture tomorrow. The simple things, the simple conservative ideas like using the jackknife to estimate the error from the residual sample, then aggregating by mean is mostly okay, but errs on the side of not spotting difference that might be there. So it errs on the side of the type 2 error. Questions? So this is partly also a research interest of mine, and I find it somewhat troubling that, I mean, if you start with a data set and then you compare methods, it seems to be one of the most natural questions of all to see, is the method really better than the other? So, you know, as a statistician, just one thing, so the hypothesis test. It's sad to see this a bit unexplored. But there is enough literature, as I've said. Okay, now, these were some details about the process itself. Now back to the scientific rationale. So it would be now point number one. What do we want to predict? So, of course, I mean, your primary hypothesis is the method can predict or can predict better than another strategy, but that in itself will not tell you a lot. So this will be the statistical question that might have been associated to a scientific question to your data. So in literature, which is mostly about modeling, you will mostly find the conclusion that the new model is better than the old models, which you should never use again. It's the usual conclusion if you do modeling research. I mean, this is useful in itself, right? If you have certain class of data sets and the new model does well on them, then of course on this type of data sets you want to use that model if you want prediction. Maybe it's not very well interpretable. I mean, usual caveats here. So one important but less often cited conclusion is that this strategy is actually better than a random guess. So if X is better than Y, but both are worse than a random guess, it might not mean a lot. So in practice, you also want to, each time you make the first one, you might also make the second conclusion. Okay, now here is a negation of the same thing. So if it does not predict then the uninformed baselines, for a methods researcher, this might be somewhat disconcerting. So this might lead to, okay, let's not publish this. But if you have a data set, if you find, say, that creeping doesn't work, or neural networks don't work really well, or random forest don't work, that tells you, okay, maybe this type of model is not good, which is, regarding your scientific question that might be associated with the data set, an interesting finding. Also, if nothing works, it might mean that the variable that you want to predict is completely unrelated to what you try to predict from. So that is also an interesting finding. Being not related is actually also something you can draw conclusions from. Or maybe it is related, but there's a lot of noise, so if you are not able to make predictions, then whatever relation there might be is covered in piles of measurement error.
But then we should also calculate the effect of an uninformed baseline, right? Then we should also calculate what the standard error is.
Yeah, sure.
If you do have.
Of course, I mean you want optimal to do a paired hypothesis test, but it's a first guess if the standard error confidence intervals are also great. Yeah. Exactly.
Sorry, another question. When you say that strategy expert is not better than uniform baselines, so say for a classification problem, will that mean that the algorithm, doesn't predict more, doesn't have a good score more than say 50% of the time? What is what you mean by uninformed baselines? How can we?
Yeah, so
equate
say the
that?
majority class of predicting the mean for regression, predicting the majority class in classification. So if you cannot find anything that predicts well, it tells you something about the data. So if you want to conclude something about the method, that might not be the conclusion that you like, but it tells you something about the data. It can tell you that the label is unrelated to the features. So for example, if you have bananas and lemons, and you choose, I don't know, the redness, this is one of your features, and either of them are red, and you try to predict the type of fruit, then you might find it's just not related.
But what I mean is more, what do you mean, what is an uninformed baseline? Is it 50%, so it has to be better than 50% of the time?
There can be multiple uninformed baselines. For a given performance measure, there will be the class of best uninformed predictors. So for regression and the mean squared error, it will be predicting the mean label on the training set.
Okay. So there are different ways to predict
Exactly.
uninformed.
And we should have some sensible approximation to making a random guess. So uninformed means it does not use the features at all.
Okay.
So if you cannot get better with using features than not using the features, then it might tell you the features have not been relevant as measured by this experiment. So it's always predicting something. So they might be relevant to something else, but just not. Okay. So since somewhat related to the point which I've mentioned, that not being able to predict tells you something also about the data, whether features and targets are related, trying different sets of features or trying different data sets in your prediction, having them or not in your predictions, in the same way may tell you about adding this additional information to your data set helps. So whether in terms of the goodness of prediction, so if it improves something, it means there is more information contained as measured by the prediction strategies. There's always also the prediction strategy involved. And if you have multiple prediction strategies, that gives you, well, depending what you do, a plausible surrogate for any prediction strategy, though not a necessary implication. So if you've tried a lot of things and you were unable to predict, it's a plausible indication that the features and target are unrelated, though it is not going to be a necessary conclusion, since maybe we just don't know the right method. But if you used a lot of methods and you didn't find anything, maybe there's nothing to find. It does not imply that there's nothing to find.
Or maybe it only says something about your out of sample data.
Yeah, maybe it says something about the validation. So the validation is also an interesting point, especially if you are in one of these correlation scenarios. If you have spatial correlation, temporal correlation, if you do the validation wrong, you may arrive at completely wrong conclusions. So for example, if you have spatial data and you completely randomly resample your spatial locations. So so say, and then you pick out your test set randomly. So if you do this completely at random, you will have a test location close to a bunch of training locations, and say, I mean, these will be similar as long as they're close, or maybe they're going to be the same. They're close as long as they are close. By this resampling, you will have put copies of training points to your test set implicitly through the correlation space, which tells you exactly what we have asked it to tell, namely if you try to predict a point from its neighbor, but maybe that's not what you want to estimate. So that's also a point of reasoning that needs to be kept in mind when setting this whole validation up. Right. So this is just what I said, using multiple predictors. And as a last point, so we have talked about this briefly in the first lecture. So even though many of the modern machine learning predictors are not parsimonious or interpretable in the sense one would like them to be, even then trying to turn the reasoning around and saying, okay, now I have a model that predicts better than the best parsimonious model that I can up with. Now, can we maybe try to find out why this nonlinear method is predicting so well? Maybe add some features here, or add a data processing step there. Can we actually approach the goodness of the really black box method and turn this into an interpretable model that is actually somewhat reversed when compared to maybe the more classical chain of reasoning, where we would first select a parsimonious model and use, say, features that you already know that will be good, and then evaluate how well it does. So instead of starting with a white box model and then, say, extending it, you might start with a black box model and try to open it. Which, I mean, neither of these strategies are wrong, as long as the reasoning, scientific reasoning, quantification behind those is correct. Questions? Yes?
Just stretch.
Yes, okay. So, stretching, shall we have a 5-minute break for stretching, or shall we just go directly to toolboxes and anyone needs to? No? Okay, so let's just go on directly with classification. Right. So we have seen unfront baseline for regression will be predicting the training mean. We'll discuss this. So in the model, nothing about the features is used, and always the same is predicted. Okay, so for classification, and essentially the resampling part is the same. Right? So just as a reminder, we want to predict a categorical outcome. Some methods which you might have seen in classification and linear discriminant analysis. You've seen this. Essentially, it's one linear method in classification where the separating hyperplanes are determined by some kind of separation criterion, feature separation measure, which is also what obtains an analytic solution. In this respect, it is quite similar conceptually to linear regression. Logistic regression also learns a linear function, now not a linear separator, but a linear predictor for the log odds of being in one class versus the other. When we obtain, so in linear regression we had the least squares interpretation, which if you follow that somehow in analogy leads to LDA. If you follow down the maximum likelihood route and try to model the odds, then what you get is logistic regression. So if you haven't seen it, don't worry, you can interpret this as a black box function, which gives you a linear prediction for the odds being in one class, or in the summary, so it gives you probabilities for each class, talking about probabilistic prediction, but you can turn it into a machine learning classifier which needs to predict the class about the probability by rounding or by putting a cutoff, at this linear function that predicts your probability. Then, as one further example, these are just examples of classifiers. K-nearest neighbors, also one example that we will use, and an interpretable baseline. So the strategy is relatively easy. So this is one of the examples, by the way, where fitting is not obtaining a parametric prediction functional. So what do you do if you have a new data point? You look at the K, say 6 nearest neighbors. You look at the majority class among the neighbors, and that's the class you predict. While, of course, you need to define what is close mean. So you can take the Euclidean distance, for example, if all features are continuous. And also you need to set K. So you need to have a look at the number of neighbors that you look, and if you look at all data, then this is going to be the majority, the uninformed majority classifier. Okay. So how do you compare classifiers such as these? So these seem to be rooted in quite different principles, and you can think of more complicated classifiers such as neural networks we might want to compare. So just in theory, the goodness of classifiers is obtained from the so-called contingency tables of predictions versus true labels. What does this mean? Well, you just count. So say, let's do this briefly. In a scenario where you have two labels, a positive and a negative one, you don't need to have that, but in general, if you have multi-class, you have a larger table, so you just count how many predictions were the one class when the true label was the one class, and so on. So if you have, furthermore, a positive and a negative label, you get true positives, false negative, true positive, and false positive. For example, if the banana is the positive class, then we'll get a table like this. And most, or virtually all measures of classification goodness are derived from tables such as this, though they are not the table itself. So as examples, so especially in the positive versus negative setting, you have sensitivity, which is a fraction of positives that are correctly predicted. And so it's the fraction of true positives among the positives. Specificity is the same for negatives, fraction of negatives correctly predicted. Accuracy is the fraction of total correct predictions. Prediction is a fraction of predictions among the ones predicted positive. So now which to use? I mean, these are a large number of measures you can use. So this will depend on your setting and the scientific question. And for classification, actually, it should be at least two that should be computed, because usually there is some kind of trade-off between, say, one or the other. So say, if you want to maximize the fractions of positives correctly predicted, then the best uninformed predictor will have actually 100%. What is the best uninformed predictor? Always predicted positive. And so if you want to correctly identify all deceased patients in a patient collective, then always predicting deceased gives you a classifier that always identifies all deceased patients correctly, though it will be quite useless for reasons you can probably imagine. So in medical prediction and screening, in the setting I've just mentioned, you would like to report both sensitivity or specificity at least, because depending on the fraction of deceased or healthy, these will only, if you look at these two, they will give you the complete picture, say, of whether it is useful in medical screening. If you are interested in finding interesting documents, data mining, say, information retrieval, you are interested in the documents that are interesting or predicted interesting. Hence, what you would like to have is the fraction of interesting documents that were retrieved plus the fraction of documents that were actually interesting among those that were predicted interesting. So you're not particularly interested in non-interesting documents in this setting. The precision and recall sensitivity are the two values that you would be interested in at least. Now if you have multi-class classification problem, say, or if you have, so quite often you have a balanced number of multiple classes, or in the typical image classification setting, what you might be interested is misclassification accuracy, precision, if there is a positive class or some multi-class variant that looks at, or that is a multi-class generalization of sensitivity or specificity, such as if f beta values that give such a generalization, or kappa, and so on. Now, as in regression, you can obtain standard errors by bootstrapping or by binomial approximation, so jackknifing and the binomial approximation are closely related. And one thing that I will mention on the next slide, so as I have mentioned, there is this trade-off between sensitivity and specificity, and some methods have a continuous tuning parameter, so you might get different pairs in the trade-off depending on the tuning parameter. Any questions about the measures that you might want? So as I said, this really depends on the setting and what you want to say about the classifier. So the most important trade-offs between two of these measures of prediction goodness. So there's the so-called receiver operator characteristics that you might have in the document retrieval setting, sensitivity versus fallout, sensitivity specificity curve, sensitivity versus specificity as it says. It's the same in medical setting. And if you have a parameter of your method, then for different parameter setting you get different points. So say blue would be one method and red would be the other method. So you get different sensitivity of this true positive versus true false. This is an ROC. So you would get different sensitivity fallout pairs for different choices of your parameter, and so you would get the curve. So you get derivative or derivate measures such as the area under the ROC curve or the area under the precision recall curve that are a summary characteristic of a method that can be further used, say, for assessing the goodness of a classifier, which are also implemented in both of the toolboxes, MLR and scikit-learn.
So which one is the best?
Which one is the best? There is no best. So it's a measure of goodness. How would a measure of goodness be best? So what's a measure of goodness for a measure of goodness, one might ask. So I would argue this is a point that the experimenter needs to decide on. So if you're interested in identifying a fraction of disease or diseased among the healthy, sensitivity and specificity is the way to go, plus possibly the area under the trade-off curve of sensitivity specific curve. Which was in document retrieval, you're interested in precision versus recall maybe. So I'm not, I'd say it's an interesting question, but I think it is beside the point. Is the experiment is about determining the goodness of the method. So what is the goodness of the method? Is there a best way to measure the goodness of the method? There's probably not. It depends on how you define goodness. Or is there? The question is partly philosophical.
So I guess you would ask, when you're doing it, would you use both or one?
Oh, both. So definitely at least two. Definitely at least two for classification. So of course, this classification error and accuracy don't count as two, as the one is one minus the other. More questions? Was there one question? Yeah, so the confidence bands for these curves could also be computed in principle. Okay, so maybe just one brief outlook slide. This will be continued in tomorrow's theory lecture. So just to make precise, I mean, I have shown some slides that look quite schematic, but if you would know mathematically model cross validation, so what are the assumptions that go in there? So the common assumption for this estimating setting that you have actually IID realizations of random variables being the whole batch of data. So actually tomorrow these are going to be random variables, but the small x would be the data you actually have. In statistics you usually measure data as random variables since it's the result of the random process of obtaining this data, which is modeled as a random experiment. And conditional on that random experiment obtaining the data, properties of various processes of analysis and estimation are quantifiable. Because if you have data that are fixed, you run into argumentative issues if you do not account for the possible randomness or measurement errors that were present in obtaining the data. So, but for cross-validation, for this one slide, it's okay to think about this as the actual data that we have observed. We're going to discuss the random variable setting tomorrow once more. So out-of-sample validation, you just split the data, you randomly uniformly sample, say, of a certain size in training and test indices, and what you then are going to do is to train the predicting function f. So the function f will be the function that is going to be applied to the unseen data, and that function will be fed, so hence implicitly depend on the training data xi, yi, t being the training set. So this will be actually a function which itself is going to be random, dependent since it depends on the training data, which is random. But for now it is fixed, so f is also fixed, but implicitly dependent on the training data. So making predictions, you substitute a data point xj into this function depending on the training data. So you could substitute one of the points that you have already observed, or you could substitute a new point. Both scenarios will be analyzed tomorrow, and why the one better idea than the other to evaluate the goodness of the function. Now out-of-sample loss, for the out-of-sample loss you have some measure, so you have some error measure. We have seen a bunch of error measures previously, right? So we're going to evaluate the mean of the empirical error on the observed test set. For example, the squared loss, popular to analyze, and this will estimate the error we would expect on any data point when here the x and y are the process from which the small x, small y were obtained. So this will be written up more properly tomorrow. So the loss we actually compute in the benchmarking experiment from the actual data will not be exactly the loss we would expect on new data, but it will expect with some degree of accuracy that will be discussed more in detail tomorrow. This expected loss on unseen data, where all the data comes from the same data sampling process. Now, this is for one split only, right? So this is conditional on the test set that was selected. So actually rerunning this and then averaging will give a better estimate more about that tomorrow, but this is what internally is going to happen in the benchmarking experiment. So this part, and repeat on different splits. Questions about this? Yes?
Is it kind of similar to the running the k-fold crossword validation, looking at differences, or like analogous to that, because that was for
Yeah, this is exactly, this,
Yeah.
this is
Classification
one fold.
versus
It's just
regression.
one fold, it's just one fold.
yeah.
So whatever this loss is, this is correct for classification or regression. So for classification, this will be just a finite set of possible numbers, and you have a different loss, which is say the misclassification loss or specificity. Well, specificity is not actually one of these losses, because you divide by the, it's a loss that is not of this form, specificity, say, misclassification errors of this form. Okay, so briefly before we start with the workshop, I'm going to explain what we're going to do. So, Tree has, I hope, shared, linked the exercises and the code with all of you. So for those who haven't worked with Python before, I would strongly suggest that you use the exercises in R. For those who would like to work in Python, well, the exercise would be essentially to do the same benchmarking experiment with the same data sets that are available in the datasets package. And use scikit-learn's two slides contain a brief intro to both. So in MLR, MLR is one major toolboxes that gives you access to this whole comparison validation workflow, and also to a lot of machine learning or the supervised learners mostly, but also some unsupervised methods using a common interface. So in MLR, each modeling strategy or each learning machine that would be, say, that we have seen in this type of slides, or the more playful Wally example. So each of these is a S3 object of type learner, say Gregor.lm. And this object has, well, so in R you don't have private functions, but you have dispatch functions. So if you call train or predict with this type of model as the first argument, this will do the training or the prediction using that type of model for one certain task. And the task is also an S3 object of its own kind, which models the prediction task. Say this data set, and we want to predict this variable from these variable, that's a task object. So if you do a benchmarking experiment, you would first, well, I mean you can do it in any sequence as long as the final result is the same, but here's a sequence which makes it clear, or which is similar to what I have explained. So first you would select the learners that you want to compare. So in this case there's no baseline here. Let's say if you would want the linear regression and random forest, you can make the learner by invoking make learner with the name of the learner, and you give it the name. The second argument is what is going to appear in the tables or the figures you make. Then you define, okay, so the first thing is defining the task. This can be done by make regular task or make classic task. So the argument of this is a data set and a target variable. All other variables by standard will be used for prediction, and the ID is for giving the task a name that will appear in tables or figures. The output is a task object. Measures of goodness, they have the names you would expect. So you can also, given a task, obtain a list of measures by using list measures that would be appropriate for that task. For example, MAE and mean-squared error are called RMSE and MAE, and they're measure task objects. They're also objects of their own type. So measures, tasks, and learners are all encapsulated as objects, modular objects in the toolbox. Validation setup, which is the type of resampling you use. For example, if you have tenfold cross validation, you get by calling the make resample desk, or description, short for description, and in the argument you can then select what kind of split you would like to have. So you can store that in a variable, and then the benchmark function takes as argument a list of learners, a list of tasks, a list of a validation setup object or validation constructor, and a list of measures to compare the methods on, to compare the methods by. Bn results is then an object which has all the results in a nested structured way stored somewhere. It has the predictions, it has the evaluated measures, and if you then print it, if you then run it, you get a table like this, but the object itself contains much more information. In the table, the first table you get is goodness of model statistics. So these are out of sample estimated using the validation setup on the top, and on the left, so these are the IDs, right? So ID would be the name you gave the task, and the ID you gave the learner. This will come in this table, and you can get further information. So if you want to extract the performances themselves or the predictions, say, from the different resamples, there is a number of functions that start with get BMR that can be used to get those out of this object. Yes?
So just a question, the time train, that's the runtime of how long it takes, yeah?
To train the
To
model.
train.
So there's time test and there's time all. So depending whether you want on it, so usually the bottleneck is the time to train the model in models that fit the function in the training part. But for example, if you have k-means, depending on how it's implemented, the bottleneck might actually be in the prediction part.
Why is that a goodness of model statistic?
A model that is fitted fast is good. And if you want to use the model in practice and it takes 10 days to run, and the model that does the same thing, or maybe slightly less accurate, that takes 1 second to run, might be preferred.
But the performance of the machine also, machine hardware.
Yeah, so it is. Of course, I mean, that's also a statistic that implicitly depends on your data. So, all the estimation stuff for the time the model takes to run also holds. But of course, there's randomness coming from your machine as well. So not only from the statistical part.